In this short video, we will talk about how to learn safe policies with expert guidance. Our motivation comes from the difficulty of designing reward functions in reinforcement learning. Handcrafting reward functions is difficult. On the other hand, we usually have access to expert demonstrations, and we can use methods such as inverse RL to infer the underlying reward function. Unfortunately, we run into the problem of degeneracy where there is a large set of reward functions under which the expert policy is optimal. Very often, the testing and training environments are similar but slightly different, and the problem of degeneracy becomes more prominent. In this simple example, the agent has never seen the question block feature in the training environment. Thus, any reward is possible for this new feature, and we need to handpick one. If we pick the wrong reward, it will likely cause damages to the agent or the environment. Our goal is to learn policies that are robust to reward misspecification and negative side effects. We formulate the problem as a max-min learning problem, and the agent's goal is to learn a robust policy that maximizes the worst possible reward. So what do we mean by worst possible reward? We assume that the expert policy is epsilon optimal, which means under a consistent reward, the expert policy achieves a return that is at most epsilon away from the optimal. Then we find the policy that maximizes the worst consistent reward. To understand the difficulty of our problem, it is useful to think of max-min learning as a two-player zero-sum game between the agent and an adversary. The agent chooses the policy and the adversary chooses the reward function. Both players have exponentially many pure strategies. If you want to solve the game with the standard LP formulation, the LP will have exponential size. Despite the difficulty, we managed to design a polynomial time algorithm to compute the exact solution for the max-min policy. Here we use tools including the ellipsoid method and the equivalence between separation and optimization. As the algorithm is based on the ellipsoid method, it may be computationally expensive to run in practice. Our second result is based on the online learning algorithm of Paulo the perturb-leader. We show that with high probability, after 1 over epsilon squared iterations, the algorithm computes policy that is at most epsilon worse than the exact max-min. Each iteration is computationally efficient, and we have conducted experiments in both discrete and continuous spaces using this algorithm. Thank you, and we hope to see you at NeurIPS.